Awesome. Well, thank you for joining. My name is Joey. I'm one of the founders of Pachyderm. And so my talk today is going to be geared towards a little bit of a different problem than what most of the focus of this conference has been on. And we're going to really be talking about kind of data science and what those challenges look like. Now, we're all at a Kubernetes conference, so you're probably either using Kubernetes or thinking about using Kubernetes as part of your infrastructure, and most likely that's for application deployment, right, and management. But today I'm going to kind of paint a little bit of a different picture and show you how Pachyderm actually thinks that Kubernetes can be pretty amazing fit for your data infrastructure. So just to set the stage for all of this and give you a view of why are we talking about data science in the first place, I'm going to give you a sense of what Pachyderm is. So the inspiration for Pachyderm really came from my co-founder running the Hadoop cluster at Airbnb, and we realized just how insanely difficult it is to manage both from a data infrastructure perspective as well as a data science perspective where the teams are interfacing with each other. So with that in mind, Pachyderm set out to solve one specific goal, and that was to enable large organizations to better manage their data infrastructure. Now, of course, that's not actually answering the question of what is Pachyderm. Pachyderm is an open source distributed processing framework built on Kubernetes. And just to clarify this up front, because we get a lot of questions about this, there's no Hadoop code in Pachyderm, right? I was kind of mentioning here, in a lot of ways, we are an alternative to Hadoop, and a lot of our early customers are choosing us instead of Hadoop because we fit in kind of the Kubernetes and containerized frameworks. So how does data science and data infrastructure really relate to containers and Kubernetes, right? So let's start by drawing an analogy to things we know Kubernetes is very good at, and that's managing microservices. We all know and understand the benefits of a microservice architecture, but I'm going to kind of talk through a few of them here. The first is modularity, right? So keeping every service small and modular with clean APIs to talk to each other, well, it really helps us understand exactly what's going on in that piece of the application, and it helps us maintain it and update it over time. Also, flexible tooling, right? Services can be written in any tools using any languages and run anywhere in the cluster, well, because they're all containerized, right? This is exactly what microservices is all about and how this gets to be really powerful. Also, services are highly scalable, right? You can throw a load balancer in front of it and have your application automatically scale dynamically based on what incoming traffic looks like, as well as what cluster resources are available. And finally, reproducibility. If I build something locally, I want it to make sure it runs like this, and it runs in the cluster the same way. And I want to be able to share my application, what I've built, with another developer and know that it's going to run exactly the same, and we're talking about the exact same piece. So this all applies to microservices, right? And at first glance, you might think that data infrastructure is a pretty different problem. But actually, if you start to kind of break it down, you realize that many of the data infrastructure challenges that you see can kind of be framed in the same way. So let's go about that one by one. Oops, give me a sec. There we go. There we go. So let's start with modularity. So this is a simplified but totally reasonable data infrastructure that we see in the wild all the time. And data processing, as I'm sure you've seen before, involves all these different steps. It may be ETL, database dumps, machine learning pipelines, all over the place. And each of these pieces can have totally different requirements and SLAs, and sometimes are even managed by different teams. So instead of thinking about them as a monolithic infrastructure, let's think of them as different data services, right, that basically have a data flow of dependencies between them and interact with each other as different applications that work together to build your full data infrastructure. And this lets us break down each of these individual pieces into bite-sized chunks that, again, are easier to maintain, easier to update, and each one can better suit the very specific purposes that it's meant to be. The next piece is flexible tooling. So the data infrastructure world is full of libraries that are all great at very specific things, whether it's TensorFlow or OpenCV. And so of course you want to use the best tool for the job, but you need a way to manage all these dependencies so they can run in a shared cluster. This is exactly the same problem that containers solve in the microservice world, which is again a large suite of tools where you need to manage those dependencies. Highly scalable. If you've ever done some sort of data infrastructure management, you probably have seen this form of a task dependency graph, right? Different tasks have different SLAs, and so it, of course, totally makes sense to have each of them auto-scale based on new influxes of data, new processing needs, what cluster resources are available. And so because of that, again, data infrastructure also needs to be able to scale up and down and be highly available as you're going through all of these pieces. So as you can see, like, data infrastructure has many of the same challenges that application infrastructure has, and it makes a pretty compelling case to try to apply some of these same principles. And so kind of zooming back out, that's exactly what Pachyderm has done. So to take a step back, Pachyderm started to think about what the specific data science challenges were. And so when we were designing Pachyderm, there were a few main goals in mind. The first was, of course, as we talked about, any tools, right? We want to allow data scientists to use whatever libraries and tools are best for their job. The second is distributed processing, right? If you're going to do any sort of data at scale, you clearly need to have a distributed processing framework so you can scale these things up and down. And the third one is actually version control for data. And this is really what we consider the hallmark feature of Pachyderm. And I'll actually dive into the details of it for a sec. But the most important piece here is that while building a product that could solve these problems and thinking about it in the framework of how would I build data infrastructure as a set of microservices, Kubernetes consistently had the answer that was just the key and really made our life easier. So let's dive in them one by one. So any tools, right? Data scientists, as with developers, come with just a crazy broad range of skills that they might have. They go anywhere from like a statistician, right, who knows R and maybe uses Mathematica, all the way to developer-oriented data scientists that use more Python and Scala, to hardcore ETL engineers who love using everything in C++ and Go as well. And we need all of this to be able to run on one unified infrastructure. But more importantly than any of this, what Kubernetes really brings is the ability to create the right interface between the data science teams and the data infrastructure teams, right? The infrastructure's job is to allow the data scientists to be able to do their work and interface that effectively. And containers and Kubernetes are exactly that great abstraction that gives us a fantastic separation of concerns. Data scientists are now responsible for everything that's inside the container, right? They can build their analysis code and have all of their dependencies and make sure they know exactly how they're transforming that data. But the DevOps team, the data infrastructure team, is now in charge of taking that container, running it on the infrastructure, making many copies of it, and making sure that it runs to completion. And this separation of concerns creates a really clean organizational process for actually doing all of this. So looking at distributed, right? So data science at scale clearly needs to be distributed and then scheduled based on the computational needs and cluster resources available. Once again, Kubernetes had a great answer to this, and it was actually their jobs API, which serves as a perfect primitive. So I'm going to kind of demonstrate this through an example. So let's say we have a bunch of images sitting in object storage, maybe something like S3, right? Kubernetes lets Pachyderm spin up many different containers in parallel, right, and assign a different shard of data to each of them. So each of those containers is running the exact same code, which might just be OpenCV doing, let's say, like some sort of edge detection is an easy example. And what Pachyderm will do is we will take each of these images and, in this example, take 1/4 of the images and give them each to each different container. So now each container gets to process kind of a stream of images in parallel. This works great in Kubernetes jobs because guess what? If container 3 goes ahead and dies, because containers sometimes do that, Kubernetes will automatically restart that. And Pachyderm basically has the logic within it to say, container 3 is the one that died. I know what data container 3 needed, so I'm going to go give that container to the new, give that data to the new container that just came up, and be able to reprocess that data and pick up where you left off. And so now you have an ability to scale this out as much as you need. This could be 4 containers, or this could be 100, giving 1/100th of the data to each of them. And you can parallelize out how this data is processed by just like having your analysis in a container. The other side, the key thing to point out here is you're actually not dealing with stateful containers, right? Really all that's happening here is you've got a container with some code in it. It's reading data out of object storage, transforming it in some way, and then writing it back. And so in this sense, like, you are transforming data, but like you're not dealing with stateful containers, and they can all be scheduled and managed wherever, and you basically get to treat your object storage as like a CDN for your data that all of your containers can access. And then the final piece is version control for data, right? So This is one of the cornerstone features of Pachyderm, and we think actually like drastically improves the data science workflow in a number of ways. Version control for developers is what lets us like collaborate on a large shared code base and not rip our hair out all the time. Imagine if you went into an organization or you were interviewing there and they said, oh yeah, we don't use version control for any of our code. You probably wouldn't take that job. Well, data scientists on a day-to-day basis deal with both code and data. And it's really important to be able to actually version both of these and at any time know that this is an exact snapshot of my data and that through this version of my code produced this given result. And then, okay, maybe I had a small new amount of data come in and I've got like this diff of data now, and I want to run that through my new, my same version of my code and get a new result. I want to be able to track how all these have changed over time. And so when you start thinking about this idea of what if we versioned data and connected that with code, you get a lot of powerful benefits. The first obvious one is reproducibility, which we've already talked about. Reproducibility lets you say, okay, I know that if I've run this code over this snapshot of data, anybody else can reproduce those results. It could be a month later, and I can say, hey, I want to run this transformation over what my users table looked like a month ago, and that commit, that snapshot of what my users table looked like a month ago is just there and available, and every single data scientist, if you say, hey, run this over the users table, knows you're talking about the exact same state of data. The next one is instant revert, and we see this in data science organizations all the time. There's a lot of time, you know, your stuff might break due to bad code or bad data, right? And being able to like instantly revert your data, just like we do with code when somebody pushes to master when they shouldn't have, you have now the ability to instantly revert that and go back to a known good state. A really common example of this is, let's say you have a large machine learning pipeline that at the end of the day builds a fraud model, right? And you've got that fraud model that you're now pushing out as a service to have traffic hit your server and like decide whether or not it's fraud. Well, if something goes wrong with your input data or maybe your code and you deploy a fraud model that's incorrect, the ability to be able to say, oh, just like instantaneously revert back and roll out the old fraud model from yesterday while I go figure out what the heck went wrong becomes incredibly powerful. And always knowing how that has changed over time, to be able to track that gets really powerful. The last piece is data lineage. And this is kind of a concept that in the data science world is starting to get a lot of traction right now, also like thought of as provenance. And basically what this lets you do is it lets you say, here is my like raw input data. And here is all the, might be 50 steps of transformations that went down to then finally produce this final result. And it might have taken in data from a ton of different sources and pulled together all these different things. I need to be able to track every single step of that, because if at the end of the day, I get to a result and I can look at that graph and say, there's no way this is right. How do I go back and debug all of that and audit that whole trail of how my data has changed and all these different pieces of code that would have transformed it? And when you think about having your data versioned, including all of these intermediate steps, you now have the ability to really do that. And it makes the iteration cycle for developing data science just incredibly much faster and very powerful. So data versioning comes with its challenges too, as you might expect. The biggest one is that if we're tracking changes and diffs of files, this creates a lot of metadata that you need indexed and readily available for fast lookups. Well, as you might expect, what you'd want to use for this is a database to store all of your metadata. But this causes a whole bunch of problems. But once again, Kubernetes showed up and saved the day because they released pet sets and persistent volumes. And in Pachyderm, basically that's exactly how I would do it. We have a metadata database that stores all that information and like basically controls the metadata around how files are versioned and diffed. And that's run as a pet set, each with a persistent volume, and this now becomes highly available in Kubernetes, and you get to run it right there. If you need to, you can always take that and sync it back to something like S3 or your object storage if you want to make sure it's super persistent, but Kubernetes does a pretty good job of it on its own. So let's take a deep breath for a second, kind of stand back and think about the kind of worldview we've built here. We want to be able to run your data infrastructure like the way you run applications, right? There is a world where that can really be possible. That includes modular services for your data infrastructure with clean abstractions between each of them, flexible tooling so your data science team can use whatever it wants and combine and compose all these pieces together however they like, highly scalable and dynamically scaling, in fact, to change as your data processing needs evolve, and of course, reproducible. And that includes data versioning, so that way you can track how things are changing over time and actually have your data reproducible in addition to your actual code. And we want to do all of this with one unified infrastructure, and because of the power of Kubernetes, we actually can. So, of course, if you're excited about building your data infrastructure in this way, and you like the idea of saying, okay, I'm used to running my application infrastructure as a set of microservices, let me think about my data infrastructure in a similar format, you should absolutely check out Kubernetes and try thinking about setting your setup this way. And you should also look at Pachyderm, because we basically build a framework for doing it in exactly that sense. Cool. That's the end. I wanted to give a lot of time for questions, because I tend to get a lot, and I went pretty fast there. I couldn't hear that last part of that question.
Like the example of where would one store huge logs?
Oh, okay. So the question was where would one do something that store huge log files and such. For us, we actually do that in object storage as well, and I've found that most object stores are actually quite able to handle that in a reasonable sense. These files, you can always break up these files in ways if that was a problem. What have you experienced specifically that causes problems for that?
Well, I've never tried it. I'm just used to traditional Hadoop things where HDFS is really great at storing these logs.
Yeah, object storage works great for this. Honestly, big files work perfect, and we've had no problems with it so far. Is that a question over here?
Data versioning, is this done by the actual application, or does Pachyderm do any sort of timestamp checking or something?
Yeah, the question was how's the versioning done? Is that done by the application of Pachyderm? The answer is that's done by Pachyderm. And so Pachyderm, actually, the way we do this is there's kind of two ways we version things. So we're basically we let you structure your data in terms of commits. So you have a set of files, and that'll be commit 0. And then you may add files, overwrite some files, append to the end of other files. And we store all of those changes that you made to the files as a diff, as a new commit that's overlaid on top of that. And so, in fact, from a data science code perspective, your code doesn't really have to be super smart in terms of doing anything with versioning. Pachyderm exposes the data to you in this versioned way. And so let's say you have a huge log file and you've appended 1% more logs at the end. Pachyderm will automatically be able to say, okay, I want to only show this piece of analysis, the new log files, because I only need to process the new logs, right? And so Pachyderm will kind of expose exactly the right data for you inside the container.
Doesn't this become unmanageable if you have a continuous stream of logs happening all the time?
Yeah, so when you have a continuous stream of logs coming in, basically the way Pachyderm handles this is you can just make commits at whatever frequency you want. And commits actually are very low overhead overall. And so we have production users making a commit every minute or commit every 30 seconds. And so you can make commits all the time, and now your logs are just constantly appending and broken up into these 30-second chunks, each of which gets processed downstream.
You don't expect the pre-processing or buffering up all the logs to have smaller commits or whatnot so that you can have less versions to store less.
You can do that if you want. You don't have to. Pachyderm, if you're just appending log lines constantly, there's very little overhead to doing that as aggregating all the logs for an hour and making commit versus doing a commit every minute just as that's coming through.
I have another question.
Sure.
How does it scale, Pachyderm? Or what is it running? Like a pod inside Kubernetes?
Yeah, so the PacD node itself, which is kind of the coordinator for all this, is just a pod in Kubernetes. So you can scale that out and run that as much as you need within the cluster. And then Pachyderm itself scales great with Kubernetes jobs, right? You can spin up thousands of Kubernetes jobs all at once, and Kubernetes will schedule all of those and figure out all where you go. So we get all the scaling benefits from Kubernetes, and Pachyderm itself just basically coordinates this and assigns shards of data to sets of containers. It's great for parallel workloads. If you have things that can't be parallelized very well, right? So some machine learning models, right? You can't parallelize that. you're not going to be able to get the benefits of running this in distributed fashion, but you can still throw all of this at a single big beefy box within Pachyderm, and that's totally fine, right? And so Pachyderm works really well actually for like quite heterogeneous, like huge data sets where you might have this piece over here that is all has to be single thread, right, on like big beefy boxes, and this thing over here can be really parallelized, right? You might have a map job, a map style job that can be incredibly distributed, but then you've got to reduce where you've got to aggregate everything all together, and like that, both of those setups work perfectly fine in Pachyderm. We give you same style map and reduce primitives that you might be used to from Hadoop to run exactly that. Yeah.
And they kind of like had a much harder time than the engineers trying to wrap their head around this. So I guess I probably have, my question would be that, what's your experience of data scientists adopting Pachyderm and using, this whole way of doing things?
That's a great question. The question was basically that as an infrastructure side, you guys kind of have a good picture of Pachyderm, but oftentimes presenting this to the data scientists, they have a hard time kind of wrapping their head around all of that. Yeah, so at the kind of early stage we're at now, that's definitely something we've seen occasionally. Oftentimes, especially data scientists who kind of lean a little bit more towards the developer side of things, find this to be a very powerful interface. One of the things we're starting to build now is the actual native, let's say, supporting Jupyter notebooks, where you can just have a Jupyter notebook, run that directly in a container. And as far as the data scientists are concerned, their interface is exactly the same. The only difference is now in that code repo, there's also a Docker file there that builds the whole thing into a container, right? And so making that story very, very clean for data scientists definitely is something that we're continuing to make better. On the flip side, when you're talking about being able to version data and think about how data is built into these snapshots, data scientists tend to glom onto that right away and say, oh, that would be amazing, right? Most of a data scientist's job is actually not spent in terms of time doing the interesting mathematical operations that they're great at. It tends to be a lot of data munging and testing and trying to figure out how do I downsample the right stuff, get this to work locally, and then figure out how to either myself or work with the infrastructure team to get this to work actually in the cluster. And when you can say the exact same Python script that you wrote locally and that runs locally, that exact same thing is now what you send off to the data infrastructure, and that's going to run in the cluster. It could be distributed. That now starts to feel very powerful, right? And that Python script, by the way, when they were running on their laptop, was probably reading and writing just local files. That's actually how Pachyderm works itself too. I was talking about this with a gentleman here earlier. Pachyderm basically takes the data in the distributed file system, right, in the object storage, and mounts it locally as a local file system inside the container, right? And that's how we divvy up what data goes into what container. And so the idea that Python script still just reads and writes local files, and that's the only cognitive overhead they have to think about in terms of accessing their data, that starts to be a pretty powerful way to think about things. That's a great question. So right now, the auto-scaling pieces of this are pretty primitive. Pachyderm will basically parallelize for each pipeline, for each state task in that DAG. You can set a parallelization factor, and Pachyderm will try to spin up to that many containers in terms of how much they want to parallelize that. In terms of how Kubernetes now wants to manage its resources, that really comes to how you auto-scale the underlying resources that Kubernetes manages, right? So if you wanted to, for instance, say, oh, we've got a bunch of new processing coming in now, Pachyderm's trying to schedule a ton of different containers, Kubernetes might say, okay, I'm going to go out to the spot instance market and bring in a bunch of new nodes and spin that up, and that's how I'm going to be able to fan out all these workloads. Pachyderm, on the other hand, really just thinks about it from the infrastructure perspective, how parallelized do you want this to be? Okay, we're going to try to schedule that much with Kubernetes, and if that's not working or things are running slow or things can't be scheduled, we can kind of scale that up or scale that back. Yeah. So actually, pipeline configurations in Pachyderm work exactly. It's just a JSON file that you put in, and that's a. Yeah, in terms of like how you specify your pipeline in Pachyderm, like that's it. And then you've got that JSON file, specifies the name of your pipeline, what image you want to use and the registry you're pulling it from, what functions you're going to call within your code within the container, and then things like the parallelization factor. How do you want your data sharded, right? If it's a map style step, like the images example I talked about, you don't care which images go where, right? You just want them, they can be all spread out. If it's something more kind of reduced style where you need an entire file or a group of files all need to be seen by a given container, you specify exactly that kind of stuff right there in the JSON file, and Pachyderm will make sure to keep all of those things together as it shards it out. Anything else? Yeah. It's a great question. So the question was, how does Spark work within this framework? So right now, we've got a couple customers that are kind of playing around with running a containerized Spark cluster and like running that within Pachyderm. One of the things that we're in the process of building is basically what we think of as a services primitive. And what that lets you do is you can have these multiple stages of your pipeline, and one of the stages can be a service that basically lets you say, okay, I've got this data in Pachyderm as my input data. Let me push that over to a Spark cluster that I can spin up right now to process all that data, and then Spark will write that data back into Pachyderm and then continue downstream from there. And so this is something that is very easy to do. Pachyderm we think about it all the time as has omni adapters on all ends, is that you can basically have a pipeline that just reads and writes data out from anywhere, right? And so it's very easy. Spark can already read out of object storage. It becomes very easy now to basically push information over to a Spark cluster, do all your computation in that sense, and then push it back into Pachyderm and make sure all of that is still versioned. Yeah.
So the incremental diff approach, I'm assuming for certain jobs that probably fits pretty nicely. But for certain other jobs, it sounds like there might be it sounds like you're doing a map and you might need to do some kind of reduce.
Totally. Yeah, so the question here is basically around how Pachyderm thinks about diffs and how that kind of translates into doing what we think of as incremental processing. And your comment is exactly right. Not everything can be done effectively in an incremental way, right? I mentioned kind of in passing during the talk that, oh yeah, we can say, oh, there's 5% new data, and I don't actually need any of the other data. Let me just process that new 5%. And because Pachyderm is aware of what data has changed and what data is new, you can be really smart about that. And for things like log lines that are just being appended, this is trivially easy now. You can just say, okay, this is the new data that you want, only process that. For some types of computation, you do need that all of the data, right? If you're doing, I don't know, I'll just say I have a bunch of numbers and I'm doing a median, right? I need to have all the data the whole time there. And so because of that, you can't really leverage the incrementality. Kind of the way we always joke about this is Pachyderm can't solve math for you, but it lets you optimize it when there's opportunities to do that. And there are actually surprisingly a lot of opportunities and a large swath of things that you do in a typical data science workflow do fall under things that can potentially be distributed as well as can be incremental. There's kind of a class of things that we think of as online algorithms that work in this way, and happy to kind of dive in and talk about more about what things work really well, what types of workflows work well in that framework versus kind of more of a typical framework where you just crunch through everything again from scratch.
Related to Kubernetes, how does Pachyderm split the data into partitions? For in a sense, plot left manually to learn split the data
So I think your question is basically how does Pachyderm think about splitting data relative to Kubernetes jobs? Yeah, so the way we think about it is if your parallelization factor for a given task was 10, right? So we're going to spit up 10 containers now. Pachyderm will take all of the data you have, and let's, again, say it's a map step like those images, so the images can go wherever, right? We will basically take 1/10 of the images, and we can just use hashes of the file names to do this, and split them up into shards 0 of 10 or 0 of 9, right? And split those all out. And then we'll basically say okay, this container here, right, is now responsible, is container 1, and this is responsible for that 1/10 of the images. And if that container dies, we now know, okay, that data now needs to be scheduled on the new container that Kubernetes brings up. And so Pachyderm itself kind of is the part that does the sharding in terms of figuring out here's how many containers I have, how do I want to split the data. Kubernetes jobs, as far as the jobs primitive is concerned, it just knows that I've got 10 containers and all of them need to run to completion, or I need to actually run to completion 10 total times in order for me to call this whole job done.
So the question was like, do we define it on the always on completion, or what we want?
Oh, how that sharding is done? That sharding is actually defined in the pipeline spec. So when you define your pipeline for Pachyderm, that specifies like here's where my input data is and here's how it can be split up, right?
Kubernetes with the pipeline defined as the one pod, like the switch map, and if you launch that Kubernetes pod, and it's not the pipeline, the Pachyderm pipeline was defined Kubernetes pod role is.
I'm sorry, I couldn't quite hear there.
You have a pod, you have like all the Kubernetes syntax involved.
Yeah.
Command, whatever.
Yep.
So if you have a pipeline, Pachyderm pipeline with the data split, like the partition, how do I define it in my pod spec? I guess that's my question.
So yeah, so Pachyderm kind of does that for you. So you don't have to define your pod spec for your pipeline, and you basically specify the pipeline part in Pachyderm, and like I said, that specifies an image, and then Pachyderm will spin up those pods and containers that now like get run. So you don't actually have to specify the pod details as part of the pipeline, both in Kubernetes and Pachyderm. You just do that in Pachyderm, and Pachyderm will build all of the right Kubernetes pieces for you. Anything else? Cool. I'm here, I'm around, I got the big green shirt on, so happy to answer more questions. Actually, we got one more. It's completely reliant on Kubernetes scheduler. Yeah, so I mean, that was kind of one of the big design premises of Pachyderm is like, let's not build everything from scratch, right? Hadoop had to build all of the distributed systems primitives and schedulers and Zookeeper and all these pieces, and then kind of go solve the big data problem. And Pachyderm's approach to this has been, Kubernetes gives us almost everything we need to be able to like solve this from a distributed systems and scheduling perspective. Let's just focus on what would a fantastic interface be for data scientists and data infrastructure teams to now like build processing pipelines. Cool. Yep.
I'm not quite sure what you're telling me this version of data looks like. Are you saying you've got like a new volume type or something, or you work with a variety of existing ones, or I guess there's two questions, right? What do you do with what volume types you're talking about, and how does the versioning go?
So the versioning itself is done on files and in object storage, right? So basically, we have a couple different flavors of versioning, and I'm happy to dive into more of these details offline if you want. Basically, we have file versioning, right? So we know if you've like overwritten a file, if you added a new file, if you've deleted a file. Similarly, we also have append-based versioning. So if you add new lines to the end of a file, we know that like this is now the diff, right? So file foo in commit 1 was these 100 lines, and file foo, if you read it at commit 2, is these 100 lines plus another, maybe another 50 lines or something there. And so that's how that diffing is done. We are in the process of building now the ability to do kind of more sophisticated things like line-based diffing for text files or something like that, where now you could update the middle of a file somewhere and you'd be able to see that as a diff in Pachyderm.
I guess I assume that you were the application code on the other side of your line. Your data scientists is to write applications that deal with stuff mounted in containers as volumes.
We basically use a fuse volume that gets we use fuse to mount that data inside. It's not actually a persistent volume that's mounted to the container.
So you're not using Kubernetes volume.
I don't believe so. I'll be honest. I'd have to ask somebody to like go through the details of exactly how that works. If this is something that's been kind of changing recently, so I have to look into that. Happy to follow up with you offline on that. Anything else? Awesome. Thank you so much, guys. Appreciate it.